he then joined IIT Delhi, but then he left for US. He did his bachelor from MIT and PhD from Harvard University. And after that, I think he was at Yale University for many years. And now he is a Herschel Smith professor at Harvard University. So, Professor Sachdev has won many awards. So I think list is too long to mention. Only thing I will mention is that he has won Drake Medal from ICTP, which is second to Nobel Prize. And he has also been awarded Onsager Prize by APS. He has also, held many chairs. He is members of many academies, and he has won many more awards. So I think I'm not going to list these awards. So he's actually one of the focus area for him has been the quantum phase transitions, and his book on quantum phase transitions has been used by many universities to teach this subject. Anybody who wants to learn quantum phase transition has to consult his book. But actually, apart from that, other area of his interest has been to look for the consequences of many electron entanglement to the properties of macroscopic realistic system. So, and he has also found many novel phases of quantum matter. Apart from that, I think is well known for SYK model, which is an exactly solvable model, includes quantum entanglement. And this model has been used in wide varieties of areas, including to understand the properties of black hole. So I think his interests are just too diverse to discuss. So now, without much ado, I will now request Professor Sachdev to give his colloquium. Thank you.
Thank you very much. Can you hear me all right?
Yes.
Yeah, okay. So it's Professor Roy, right? I'm sorry. Okay. Well, thank you very much, Professor, for the kind introduction. And I'm very happy to be online at TCG Crest. Hopefully someday I will be able to see this new institution in person. Okay, so let me share my screen now. Okay, so can you, let's see. Yeah, okay. All right, so can you all see my screen clearly, or is there anything blocking it?
Yes, we can see this.
Okay, let me, one thing. Okay, all right, thank you very much. So I'm very happy to be here, and I'll talk about mainly focus on work on the cuprate high temperature superconductors and how that's connected to various recent and not so recent ideas on many particle quantum mechanics. So this is the material that's been the focus of so much interest since their discovery in 1986. The cuprate high temperature superconductors. They're still the very best superconductors at ambient pressure. And they were the first materials that could be bulk superconductivity in materials that are can be made now into long wires above liquid nitrogen temperature, excuse me. But theoretically, the discovery of these materials led to, you could say, a huge revolution in solid state or condensed matter physics, because pre-discovery, essentially all the discussion of bulk materials was in terms of an independent electron picture. And then, of course, the culmination of that was the pairing of electrons in the BCS theory of superconductivity. But post 1986, the effort has been really to to understand the consequences of entanglement, which go well beyond the standard Hartree-Fock style independent pictures. And this has come a long way. So we've been working on it for nearly 40 years now. And I'll try to just give you a summary of where we are. Okay, and let me just very briefly mention, there's potential for life-changing applications from these materials. In particular, these magnets are being used. Here's the wires of YBCO in various configurations for fusion energy because of the ability to create large magnetic fields in a compact area, a relatively large area. And these are the slide pictures from a company that's trying to make this commercially viable. But I'm not going to say anything more about that. So turn into the microscopics. So these are complicated materials with lots of elements in it. But fortunately, all of the interesting physics, I think the universal agreement, happens basically on a single layer. And the layers are weakly coupled to each other. And each layer has a square lattice of copper atoms. And that's how I'm going to just simplify it. There's oxygens between them, but I won't say anything about that. And at a certain density of oxygen doping, the X's, this forms an insulator. And in that insulator, there's only one electron that's active on each copper site. This is in a certain d orbital of the copper. And because of the Coulomb repulsion between the electrons, they're frozen. The charge is frozen with one electron on each side. And their spins are antiferromagnetic. So this kind of arrangement, like a chessboard, has been seen in numerous experiments, and also lots is understood about it. But soon after the discovery, even though this material is now known to be an antiferromagnet, there was a very bold suggestion by Phil Anderson and Bhaskaran that really the correct state of the electrons we should think of was something they called a resonating valence bond state. So today we understand this resonating valence bond state as the simplest early example of a wide variety of phases of matter, which are called quantum spin liquids. And I'll just give you a quick introduction to what a quantum spin liquid is in the context of the RVB state. So the RVB state postulates that the electrons pair up to form singlets. So each ellipse here is a singlet of a pair of electrons. And the ground state is a superposition of different ways to form singlets. So here's one way to form singlets, but there's many others. And all of these combine to form a state that's macroscopically large. There's an exponentially large number of such dimer configurations, e to the 10 to the 23. And all of those are superposed in a coherent manner. So this has some similarity to benzene, which has only two configuration of valence bonds, and what chemists call resonating valence bond 2. But here, this is generalized to a much, much larger set. So this is a state that today we say has long-range quantum entanglement. And we have many ways of characterizing this state. But I think the most fundamental is the following. So let's take the state and try to create an excitation. So the simplest thing you can do is take a singlet and you break it into a triplet of spinor halves. But that's not the elementary excitation of the state. You can imagine moving these spinor halves so that one of them runs off to infinity. And now we are left with just a spinor half on its own. And this is the true excitation of the state, which can move around and carry spinor half. So what you notice as it's moving is carrying spinor half, but not moving any charge. And that's a strikingly new type of particle, which we now call a spin-on. And understanding the structure of states with spin-ons is really a big part of what I'll be talking about. So each such spin-on is sometimes called an enneon, because there's many such excitations, and their fundamental property, as I've illustrated here, is that you cannot create a spin-on on its own, or any local operator. A local operator will always create pairs of spin-ons, and so that's you could say a defining property of an anyon, that it cannot be created by any local operator. And that's really the fundamentally new thing that this RVB type state introduced into physics. Today, of course, we have many such states and well understood, and there was a remarkable suggestion by Kitev that these kind of states with anyons or spin-ons can be used for quantum error correction. And that's because it's very much connected to the previous property. Since you can't create any anyon with a local operation, that means that local operations is not going to even destroy the anyon. So the anyon is just really always there. And so if you could hide the quantum information in a superposition of the anyon sectors, then it would be protected. Okay, so I'm not going to say much more about such states, but today I would say that such states are well classified in 2 dimensions. And the original Anderson Bhaskaran RVB state is recognized to be what's now called the Z2 spin liquid, which we proposed in 1991. And it has the same anyon structure as the toric code, which I imagine all of you know about. And these have been recently, this toric code has been implemented in Google's quantum machines these days. So this is one can claim a remarkable impact of these ideas coming from condensed matter physics, which have strongly influenced developments in quantum information science. But these particular ideas, in particular, these types of states have really not led to too much insight into really understanding experiments on the high temperature superconductors. And so what I want to claim today is that we have to really think about spin liquids of a different type, a critical spin liquid, and also a critical charge liquid, of which the SYK model is a solvable example, which are quite different from the gapped states I just told you about, because they don't have any particle-like excitations. They're so strongly interacting that they don't have excitations that are bosons, anyons, or anything. They're really extremely strongly entangled, and understanding such states has been also a major effort in condensed matter physics in recent years. Okay. All right, so now let me get to a little bit to the nitty-gritty. So here's the phase diagram as a function of electron concentration on each square lattice of copper atoms, and here's temperature. So I'm going to focus mainly on the metallic phases above the superconducting phase here, although we've done a lot of work even on the onset of superconductivity. And let me begin with the simplest one, which at high P, which is a Fermi liquid. In particular, the basic property of this system here is that it obeys the Luttinger relation. So here, at these values of P, the antiferromagnet is at P equals 0. At these values of P, you don't want to think in real space, you want to think in momentum space. You think of electrons as just waves with a fixed momentum. And the exclusion principle tells us that they're just going to occupy the lowest energy momentum state. So this is kx and ky, this is momentum space here. And what we know from experiments is that these states here inside this bright line are occupied and these are empty. And the boundary between them is what's called the Fermi surface. And the fundamental Luttinger statement is that the area enclosed by the Fermi surface is independent of electron-electron interactions. So that's quite remarkable. The shape can change, but the area enclosed by the Fermi surface is if you wish, a topological invariant. And that indeed works very beautifully here at these values of P. You do indeed see in measurements that the number of the area of this region is exactly as needed to have 1 minus P electrons. Okay, but when you go to lower doping across TC, you seem to get a very different state, which never been anticipated theoretically, really. And here there's no obvious Fermi surface. And I'm going to present an approach where we're going to explain it by a state that we call the fractionalized Fermi liquid, or FL star for short, which is a metallic state but does not obey the Luttinger constraint. And it's able to do this precisely because there's a background of a critical spin liquid, which is the key, I believe, to understanding many of the properties of these materials. And then finally, if there's time, I'll say something about the intermediate strange metal phase. And this is where ideas on the SYK model will be important. This picture is just a fanciful description of there's a duality between electrons obeying strange metal-like physics and the near horizon physics of certain black holes. But I will not say much more about that in my talk today. All right, so let's go back to the pseudo gap, and let me just tell you a little bit more about the experiments. So I've already shown you this plot of the so-called Fermi arcs, where there's no Fermi surface, a rather mysterious contour of the zero energy excitations right at the boundary between occupied and unoccupied states. So what is this due to? Okay, but there's a very different sort of picture that's emerged from magnetotransport experiments. Here's one experiment, which I won't say much more about other than to cite it because it was very important. What you're doing here is you apply a magnetic field at some strange angle. And this is a picture of the Fermi surface. I showed you these Fermi surfaces earlier on the large doping side. But this is they're also warped in the third the direction perpendicular to the square lattice. And you change the angle of the magnetic field and you measure the resistance in this direction. And this turns out to be a beautiful way of measuring something about the Fermi surface. I won't go into the details, but I want to highlight a very recent experiment on something called the Yamaji effect. So this is the same basic experiment carried out in a slightly different cuprate superconductor at the doping P of 0.1 above TC. And what they observed is something called the Yamaji angle. So I won't go into the details of this, but it's basically a special angle of the field at which this area of electrons orbiting perpendicular to the field doesn't change no matter where you put this orbit. So it's a purely geometrical factor. And when that area doesn't change, the electron doesn't want to tunnel in the third direction. And so that turns out to be a very large resistance. So at certain angles, you see a peak in the resistance for electrons flowing in this direction. And this has been seen in other simpler quasi-two-dimensional compounds. But now, for the first time, it's seen in a cuprate. And here's a picture of the Yamaji peak. So it doesn't look that impressive, but you can see that theoretical modeling can capture more than just the peak for different angles and different fields. So again, I won't go into the details of experimental interpretation, but just to say that from the modeling and the Yamaji result, you don't really much modeling, just knowing the value of theta Yamaji and knowing the value of the c-axis spacing, you can read out the area of the Fermi surface. And so they assume some elliptical Fermi surface, presumably there's 4 of them for different reasons. And they concluded that each such area pocket encloses 1.3% of the area of the Brillouin zone, which is this. Okay, so just remember that 1.3%. So that is I claim a key clue to the nature of the state of these materials and its quantum entanglement. Okay, so what I've summarized is this remarkable tension now between photoemission experiments, which see Fermi arcs, and magnetotransport experiments, which see hole pockets. So now let me just give you some very simple pictures of how we're going to reconcile this and different proposals for what the pseudo-gap phase is, and in particular the FL star theory. So if you had the electrons just moving freely, or holes here, after I'm thinking in terms of holes, then we know that the area enclosed by the hole layer, these empty states here, should be 1 plus P over 2. P, because the density of holes with respect to the fill bands is 1 plus P. And the factor of 2 here because of spin. So each state momentum has both spin up and spin down. And that's indeed what you see in the experiments at large P. Okay, now let's go all the way down to 0 P. And there you have the antiferromagnet. This is an insulator, so there's no Fermi surface. Now you put in a few holes of density P, but at very low densities where the holes don't disrupt the antiferromagnetic order. Then these holes will occupy, in simple calculations you can do, these ellipses. And now we can ask, what is the area of each such ellipse? Now, because of the broken symmetry, the Brillouin zone is halved into the diamond shape here. So there's really only two hole pockets. And there's P of them, P holes, and you have a degeneracy of 2 from spin. So the total degeneracy is 4, again, 2 for spin, 2 for valley. And so the area of each pocket is P over 4. All right, so now let's take the RBB state, or really any general spin liquid, where the spins form singlets. I only show nearest neighbor singlets here, but the argument is extremely general. And you put in a density P of these holes. So what we argued was that even in such states where you have the spin liquid around, and you have these excitations. So these holes now carry, as they move around, they carry charge E, but no spin. So they are what's called holons. So these are anyons. So even in these anyon liquids, there should be a modified Luttinger relation. So the presence of a spin liquid modifies the Luttinger relation. That's kind of what was argued in this paper with Senthil and Vojta. And in particular for this holon metal shown here, again, the area enclosed by the Fermi surface should be just P. The Luttinger would say it's 1 plus P, but now we say it's P because of the spin liquid. So it's a non-Luttinger area. Now, again, there's, in any simple calculations, you find 4 hole pockets. So, but now each of them is distinct because there's no broken symmetry. But they're spinless. So there's no factor of 2 for spin, but there's a factor of 4 for valley. So again, the area is P over 4, but that's an accident. It need not, for different reason, it's the same as the antiferromagnet. So this state and this state have basically the same area, but that's just an accident. So finally, let me introduce the FL star state. So now this spin liquid also has spin-on excitations. So you can break the singlets into spin a half spin-ons. And each spin-on can now move around. But let's imagine they all move around and find a holon. And then they form bound states. And if you gain some energy in this bound state, or some people call it a magnetic polaron, it's a bound state of a vacancy or a holon and a spin, then the system will be willing to pay the price to create the spin-ons because you gain that energy back when you form the bound state. And there's various arguments one can make that that's always the preferred thing to happen. So now these bound states can move around. And these bound states, as they move around, they have charge spin a half. They also have charge E. So they're just like electrons or holes. And their density is P. And so again, by the arguments we made, they should form a Fermi surface if they're fermions. They are definitely are fermions. And so what is now the area of the Fermi surface? Well, there's 4 pockets again, but now they spin a half. So you get 4 for valley and 2 per spin. Area is P over 8. Okay, so that's what these basic simple pictures show you. And these spin-ons are still present in this state. So this is really not a Fermi liquid. That's why we put a star on it. And it also doesn't obey the Luttinger relation. Okay, and so this was something, this P over 8 or delta over 8 was something we predicted way back in 2007 by very different methods. And that makes a point that these simple pictures are just to give you an intuitive feeling, but there's a much more stronger, a deeper argument that one can make that these are robust values. It's a kind of a topological argument. And so, so it's very nice to have this quantization here, which we are so familiar in, say, something like the fractional quantum Hall effect. But even these metallic states have certain quantization features that are extremely important. All right, so now I can go back to this 1.3%. And of course, I was very happy to note that P over 8, the value we predicted, is 1.25%. And it's very different from the values in the other theories for the pseudocap. Okay, so one can say, and this P over 8, as you have seen, is really a consequence of the many-body entanglement. There's no simple state you could get from density functional theory or Hartree-Fock that has this area. It's just not possible. So this is really the best evidence yet for fractionalization in the cuprates. Okay, but that, so we've understood the magnetotransport, we believe, but that still leaves the problem of the Fermi arcs. Let me just look up the time. Okay, I'm doing okay. So, which was seen in photo emission. How do you understand that? So do you have pockets or do you have arcs? Well, it turns out you can have both. And to understand that, we really have to now do a serious theory of this background spin liquid. And this is a task that, as you can see, we've been working on the community since from 1988 all the way to just last year. And it's taken that long to really have a good understanding of what is a good candidate from the theory side for a spin liquid on the square lattice. It's taken also a lot of beautiful numerical work. This last work is numerical, but there's many others I have not cited here. And the conclusion is that the most likely state is the following here, which actually goes back to very early work of Ian Affleck in 1988. So this is a state where you take these spin-ons and you assume that they're essentially free to begin with, and they move in a background pi flux on the square lattice. And when you do that, and you look at the dispersion of free fermions on pi flux on the square lattice, you get 4 Dirac nodal points. So that's very similar to electrons moving on a honeycomb lattice in graphene, giving you 2 Dirac nodes. Here also there's only 2 because of the pi flux. Except these are fermions that carry spin but no charge, whereas in graphene, the Dirac particles carry spin and charge. So because they are fractionalized, they must couple to a gauge field, and the appropriate gauge field is in SU2 gauge theory. So we have to study something that's actually fairly close to our theory of quantum chromodynamics in 3 spatial dimensions, where we have SU3 gauge theory with NF equals 3 nearly massless quarks. And here we have SU2 gauge theory with 2 exactly massless spin-ons. So this is the theory that we really have to apply to the cuprates, and that's what we've been working on in recent years. So in particular, there's a theory for FL star in a single band model, which is something we call the ancillar layer model, which I will not talk about. which was introduced in this paper with Yahui Zhang. And that gives you these pockets of area P over 8 to begin with. But then it also gives you this background spin liquid, which of Affleck and Marston, which has these 4 nodal points. And that's the starting point. And now we have to couple them all together. And it turns out the way you couple them, just like in particle physics, you have to introduce a Higgs field. So in the theory of weak interaction, the Higgs fields couple the neutrinos and the electrons. And here the Higgs field couples the electrons of the hole pockets and the spin-ons. So you do a theory of this fluctuating Higgs field, thermal fluctuation of this Higgs field, and you find then something very satisfying. That's what's shown in this recent work in a collaboration with Sayantan Sharma's group in Chennai at IMSC. Let me just get a little water. So what we showed was that when you put in this full SU2 gauge theory and include thermal fluctuations, it converts these pockets coupling to the spin-ons precisely to the arcs that are quite close to what's seen. And furthermore, it can do this in a way that doesn't destroy the Yamaji type effect, the fact that you get some special angles on elliptical motion of area P over 8. In this case, we haven't actually computed the Yamaji angle in this paper, but we computed simple quantum oscillations. And we found that there were regimes where you had Fermi arcs, and at the same time, you had oscillations of area P over 8. So that at least shows that, everything hangs together. And this novel fractionalized critical spin liquid state is the key to putting everything in a nice, in a nice way. So there's lots more work to be done here, and we're also making a whole bunch of predictions. But I'm going to move on to really the other part, the other critical liquid I wanted to talk about, the charge liquid, and its connection to the strange metal. So this is the phase diagram I showed you earlier. We're going to now talk about this metal and try to explain it with an extension of what's called the SYK model. And this is work in collaboration with Avishkar Patel, who's just started at ICTS, and Ilya Estelis and Hayugo, a former student, and also York Schmalian's group. Okay, so what is the SYK model? So let me just, it's really started out as a toy model, but even from the early days in '93, we were very much motivated by the cuprate physics and formulated it in terms of a model that was quite appropriate for the cuprates in a mean field way. But Kitaev suggested an improvement, which has led to remarkable developments since 2015. So I'll mention, what I'll describe is the form that Kitaev presented it. So you imagine you have a bunch of sites, there's 19 sites, and some fraction of them are occupied by fermions. So I'm just going to ignore the spin for now. And now these fermions can move around. Normally, if you had some random matrix model, fermions would hop one by one. But in fact, we're going to only allow them to hop 2 by 2. So for example, the fermions on site 11 and 12 can jump to site 5 and 14. So there's a quantum mechanical amplitude for that, this number U, which you have to know depending on the microscopic physics. And then there could be other possibilities. In fact, we allow all of them. And the key assumption we make is that these numbers are all independent random numbers. So if they weren't independent, they're a given set. This is an impossible problem to solve. You're getting lots of entanglement, but you have a many-body space, which is of size 2 to the n, where n is the number of sites. So you can solve it, but the remarkable thing is you can solve it in the large n limit. The only assumption is that the U's are independent random numbers. Okay, so that's the form of it. And you can solve it. And in fact, the solution is not that complicated to begin with anyway. You just assume, you just do Feynman graph and expansion. So you do a Feynman graph expansion for the Green's function and the self-energy, and you average the graphs term by term. So why are we averaging? Since, well, it turns out the system has been shown by numerical work and lots of analytical work is very strongly self-averaging. So in fact, every site behaves like every other site when n is large. And so you may as well average, and the fluctuations from site to site are extremely small. So you just start averaging, and when you start averaging, you find that only one Feynman graph survives the large n limit, and this one. Like this one vanishes and then goes to infinity. So you just get these very simple set of equations for the self-energy. Self-energy is just given by this one graph, which gives you that equation. And this is the charge density. And you just have to solve these equations for mu and g of tau and sigma of tau. There's three equations for three unknowns. Okay, so why not just, we started solving these equations in 92, 93. And I thought, okay, yeah, it will be done in a few weeks, or someone's already done it. Well, neither was true. We're still understanding new things about these equations, and in hiding in the full structure of these equations, in fact, a theory of quantum gravity closely connected to Einstein gravity. But I won't go into that. What we already understood was that the scaling form the solution at low temperatures, that the Green's functions diverges at 1 over temperature, square root of temperature, or 1 over square root of frequency. And in fact, there's some scaling behavior with temperature, which gives you some universal function. Okay. So in the end, from the solution, and I won't go into further details, it gives you a solvable model of many particle entanglement and yields a quantum state whose excitations are not particle-like. So that's sort of like the pi flux SU2 gauge theory I told you about. But that theory, that earlier theory is much more complicated. We can't solve it. It's 2 + 1 dimensions. But here we can completely solve it. So that's a bit of a surprise. They have this extremely entangled, or I would say more than a bit of a surprise. We have this extremely entangled state of many electrons, which has no quasi-particle description, but nevertheless, many things are solvable. And if you try to apply a force to carry current in some such system, you'll find that, again, there's no particle-like excitation, but current is carried by an entangled quantum soup. Okay, so that's great, and we were quite excited already in '93. But nobody believed that this simple model could have anything directly to do with the cuprates. It was a nice toy model, it seemed. Well, that gave us a lot of insight, and we continued to work on it for many years. And then the black hole connection was something I proposed in 2010, and was also very exciting, and it's taught us a lot more. And through those connections, we've realized how we can really connect this up more firmly with the microscopic physics of the cuprates. So that's what I'm going to turn to. So here's another version of the cuprate phase diagram. This is a theorist version. Previously, I was showing you something that was mainly focusing on the experiment. So here, the idea is that, again, focusing on the normal state, there's an FL star state that I've told you about. And then there's the Fermi liquid, or FL state, I've told you about. So let's just imagine that both of these two states are stable down to 0 temperature. Just as a theorist, let's examine that. Then there'd be a quantum phase transition between them, because they have very different Fermi surfaces. But it's a very novel quantum phase transition, because there's no broken symmetry on either side. There's no symmetry. It's a purely topological phase transition in the structure of the entanglement of the many-body wave function. So that's the phase transition that we think is ultimately responsible for the strange matter. Now, in the real world, however, there's a lot of evidence that both of these states are unstable to superconductor. And in fact, there's nothing that happens across in the superconducting state, nothing dramatic. And that's precisely what this theory gives us a way of also doing, provided the FL star state has a transition to a conventional D-wave superconductor. And in fact, it does, and that's the part of the theory that I haven't described. Anyway, so the lesson from here is that we're going to work with this, let's call it an incipient quantum critical point between these two metals, and find a third metal in between, which hopefully looks like the strange metal. So this is again a task, enormous amount of work in the last 20 years. And I'll just tell you about, the approach that has worked, which is inspired by developments from the SYK model. So it turns out that to really understand this properly, you have to worry about the effects of disorder, impurities in the sample. And so what we need is a theory of FL star FL transition with local and spatially random interactions. And the model that works is now called a two-dimensional Yukawa SYK model. I'll show you what it is in a minute. And you just solve it exactly the way you solved by the SYK model. You take a certain larger limit and you average order by order, and I'll show you some of the results you get from that approach. So here's the model that we want to study, which is called the 2D YSYK model. So you have fermions at the Fermi surface. So this is something we didn't have in the SYK model, but you do have to have a Fermi surface. Then you have this Higgs boson, which is responsible for this transition. And that couples to the fermions by a Yukawa term, hence the term Yukawa SYK. And then in blue are the impurities. And the impurities, normally you think of them as a random potential, but it turns out to be absolutely crucial to also look at the influence of impurities on the Yukawa coupling. And this is, very much in the spirit of the SYK model, where it's the interactions that are random, not so much the potential. And so since you've learned how to solve systems with random interactions from the SYK model, you just apply the same tricks here. And what we learned was you just average term by term, and you look at a certain set of self-consistent graphs for the self-energy. And that's exactly what you do here. These are the terms that come from randomness. And this is Dyson's equations. These are Green's functions for both the fermions, the electrons, and this Higgs boson. Anyway, you solve these equations and you compute lots of other properties. That's what's occupied us for several years. And there's many things we think match the experiment. Let me just show the most dramatic. We can compute the resistivity as a function of doping or some doping-like parameter and temperature. In fact, this model also has a superconducting phase. And here we get T-squared resistivity like you get in the Fermi liquid. And this is in this region, you get what's called Planckian behavior, where the scattering time is inversely proportional to temperature. And the resistivity is a linear function of temperature. This is the same data showed here for the resistivity at different values of m/t as a function of temperature. And this looks strikingly similar to many experiments, not just in the cuprates, but many other materials. But let me just mention, I'm doing well on time, this optical experiment. So people have, through the measurement of optical reflectivity and transmission, there's very detailed measurements in the cuprates by this team of both the scattering rate of the electrons as a function of frequency and temperature, and the scattering rate as a function of frequency and temperatures collapses onto the scaling form. This form where tau is just h/t, and independent of any particular interaction between the electrons. So that's what's called Planckian behavior. And that's exactly what emerges here. And in fact, even this function f, which is this function here, looks quite similar to the experiment. So this kind of theory of spatially random interactions at the mean field level leads to really very encouraging agreement with lots of experiments. I've just shown you a little bit here. But at low temperatures, we do have to worry about breakdown of self-averaging. The SYK model doesn't break down because it's infinite range. Here, there's a local randomness, and there will be breakdown of self-averaging. And the dominant breakdown of self-averaging comes from localization, not of the electrons, but of the boson. Okay, that's again something we've been working a lot on, but don't really have time to discuss here. Actually, I made good time because I'm basically done. So I guess it's time for questions. So to summarize, this is the theoretical phase diagram, slightly modified from a paper I wrote in 2009, where just looking at the basic idea here is that there are really three different metals. There's the pseudo-gap metal and then there's the Fermi liquid, and in between is the strange metal. They meet at a quantum critical point at 0 temperature, but because all these metals have an instability to superconductivity, you don't actually see that critical point. You may see other critical points due to onset of spin density wave order, but that's not the relevant state to understand the strange metal. Okay, so what I presented to summarize is a theory of FL star, which had hole pockets and a critical spin liquid, which was an SU2 gauge theory with massless Dirac and Higgs matter. And this leads to a gapless, strongly interacting many-body system with, well, in this case, the spin-ons are, this is not quite right. The spin-ons are not well defined, but the electron, the hole pockets are actually quite well defined. So I'll have to make a correction here. But in the strange metal, there are no well-defined particles. It's a critical charge liquid described by this extension of the SYK model. And really, that's all I have to say. And here's a fanciful picture of how these strongly entangled gapless states are really the key to understanding the structure of the cuprates. Thank you.
Thank you, Professor Sachdev, for this very enlightening talk. So let's see if there are any questions.
Yeah, I would like to ask a question. This spin-spin entanglement and spin-hole entanglement, there's a resonating valence bond model. So why is the Fermi surface but the spin-hole interaction so small? It's like a spot in the middle, right?
Let's see, let me bring that slide up again. So are you referring to like this one?
Right. So the one pair is this spin entanglement, the other one is a spin and charge entanglement, right?
Okay, so you're talking about the first part of my talk or the second part of my talk?
This is the...
Yeah, so let me just summarize again then. So here, so the simplest state is this state, the hole-on metal, which was already discussed in the very early days of cuprate physics, where you have chargey fermions, which are spinless, moving in a background of RVB. And you can do certain, you have to do some calculations on how these move around and what their dispersion is. And what you find that the dispersion has minima, which are not at zero momentum. They're somewhere over here. That's a non-universal feature. Maybe in some other lattices, the dispersion minimum would be the center. But no matter what, the total area enclosed by all of these pockets should be P. So there's 4 of them, the total area, each of them is P over 4. So the universal part is just the fact that the sum of the areas is P. Now, on the other hand, what could happen is that the spins and the holes can form a bound state. They form these green objects. And these green objects can move around. And they're fermions. So they will also form Fermi surface. So what we can say now is that the total area enclosed by the Fermi surfaces of the green object, no matter where they are, should be P over 2, not P. And it's P over 2 because of spin. Each of these objects carries spin as a degeneracy of 2. So the total area, whatever they are, should be P over 2. Now, again, for microscopic reasons, it turns out there are 4 valleys at some non-zero momentum, not at 0 momentum. And so then the area becomes P over 8 per pocket. Okay. So the universal part is P over 2 for F star and P for the hole on metal. And also, I should say that the Hall effect for both of these states is just P, because that just depends on the total density of charge carrier. So there's a difference in the Fermi surface, although there's no difference in the Hall effect. Okay, that was the first part. The second part, where I'm talking about charged liquids, but really there's charge and spin. I'm really talking about electrons here. I just didn't draw spin for convenience. So maybe that was the confusing part. These fermions here, which I'm calling psi, do carry spin. And this is just an ordinary Fermi surface. This Fermi surface here is just, there you go, is just that Fermi surface. So if you take this Fermi surface and center it at that point, you get a Fermi surface here. That Fermi surface is what's important for the strange metal. And that's what I'm drawing here. Okay, I hope I answered your question there. Did I answer your question? I can't hear you.
Actually, Prof, there is asking another question that is about, you have only 2 particle entanglement, right? In SYK, for example. Why don't you have multi-partite entanglement, like 3 particles?
Oh. No. So SYK is infinite. Everything is entangled with everything else. That's the point. Once you have a Hamiltonian with 2 particle hopping, because the point is that, you know, say these 2 particles can move, but then this particle can pair with any other particle and move again. So then 3 are entangled, and then they can pick other partners. So it keeps going. You build up the entanglement in a hierarchical manner. Because the partners can split apart. They're not as if you're always paired with another one. You know, so if you had just had 2 electrons sitting there and they entangle with each other, so that if you formed a singlet here and 2 of them form singlets here and 2 of them form, then yes, then you only have 2 particle entanglement. But once the feature of the SYK is that the pairing is not fixed. Every particle can pair with any other one, and that entangles all of them. And in fact, you can also take more complicated Hamiltonians where the interaction, where the Q fermions can move with at the same time. And Q equals 2, 3, 4, and they all have a very similar picture. Q equals 1 is the one that's different. Each electron moves on its own, then there's essentially very little entanglement.
So you mentioned the Descartes.
Go ahead, sorry.
No,
The current is carried by an entangled quantum soup, we mentioned, right? So
yes. Yeah, well, that's that's
it's sort of indication of a multi-particle entanglement.
Exactly. I mean, I wish we had a better intuitive understanding, but we don't. When we think of electrons flowing in a copper wire, current flowing in a copper wire, it was just individual electrons carrying the current. What I mean by that is if you did a photo emission experiment or something, and looked at the electrons, you will really see them individually. But here, current is flowing, and you look in the microscopics as you do in photo emission in the strange metal, and you don't see individual electrons. So that's also, that was
So
inspired
what
very
do you
much
see?
from.
What,
You just see a very broad spectral function.
if you do a photo emission experiment, what do you see?
You see a very broad spectral function. You don't see, if you had individual electrons, you see a spectral function that becomes very sharp as you lower the temperature, and that doesn't happen here.
But if you carry out a photo emission experiment, you look at emitted electrons, right?
Yeah. So I mean, in fact, well, this wasn't photo emission, but the data is not that dissimilar. When I showed this, where is it? Okay. Yeah, this data, this 1 over tau, that's the scattering rate, and it's much bigger. It can become much larger than temperature of the order temperature, even at zero frequency. These scattering rates are very large, and that's an indication of the absence of quasi-particles here. Okay.
Okay. Right. So there is one online question.
Yeah, in the chat. Okay, let's see. Okay, Aditi Mandal, how would you imagine the Fermi surface for the strange metal in momentum space? Yeah, so it's very much like the large Fermi surface on the overdoped side, but it's very broad. Those lines, which are very sharp, become very broad. So it's in the strange metal region, the Fermi surface looks pretty just like the large Fermi surface. Okay, I think I don't see anything else. Yeah, okay.
Okay, so I think if there are no other questions, let's thank our speaker, Professor Sachdev again. Because I mean, he took time and got up early and to educate us. So thank you, Professor Sachdev.
Thank you for inviting me. Okay, thank you very much.
Mm.
Okay, bye.
Thank you.